but I could write it like this. From 0 till the fusion TF, right, times Cp of the solid times dt by T plus delta H of fusion by temperature of fusion plus integral from Tf to T boiling Cp liquid dt by T plus delta H of vaporization by the boiling temperature plus, so I am just adding up all these entropy terms, whatever is being added, to plus integral from boiling temperature till the temperature that I have defined, T, Cp of gas dt by T. I mean, it depends on where the temperature is. I may not have the rest of the terms. Now, I could in principle write like that if I knew what exactly is the behavior of these terms. Now, I can very conveniently assume Cp liquid, Cp gas to be almost constant, independent of temperature. But as you will see in quantum mechanics, or maybe you will not see, but it's the background of quantum mechanics, why quantum mechanics came into existence, is one of the reasons was that it could not explain, classical mechanics could not explain the heat capacities at low temperatures. Okay, so maybe I'll go through that. So, what it does, the quantum theory does is to say that your heat capacity at low temperatures is proportional to some constant A T cube. So you could approximate that A T cube for very low temperatures around 0. The rest of the heat capacities you can get. Yeah? You can get all the other quantities by experiment. Now, if you know S of 0, right, then you would know the absolute entropy at temperature T. All the while that we do in thermodynamics, and what we've been doing is delta S. That is the change in entropy going from one state to the other. But if I know the value of S naught, I'll be able to exactly say what is absolute entropy T. Absolute entropy at temperature T. Right? So, how do we get the value of S naught? That brings us to the third law. And the third law, in fact, what precedes the third law is something called the Nernst heat theorem. So, what it says, I'll just read it from the handout I have given you. The entropy changes accompanying any physical or chemical transformation approaches 0 as the temperature approaches 0. So, mathematically, delta S approaches 0 as temperature approaches 0. So, if there is a transformation from one state to the other, then let me go back. Then what we had over there was this fellow. So if I am at a very low temperature, then all I need to worry about is perhaps this one. So let me not even worry about that. Let's say that we are at 0 Kelvin. We are not at 0 Kelvin, we are at 0 Kelvin. And at 0 Kelvin, if I do a transformation from one state to the other, one phase to the other, most likely, then the delta S is going to be 0. That's what the Nernst heat theorem. Nernst heat theorem is more of experimental observation. So they go down to very low temperatures and try to change from one state to the other, maybe one crystalline state to the other, and they see that this delta S comes out to be 0. So now when it happens for almost everything, then you are tempted to say that, okay, rather than giving some particular value to entropy at 0 Kelvin, why not give it a 0? A value of 0. That's more likely rather than everything having some other constant value. And the reason is also there. Last time what you saw was that the gas, the Joule expansion experiment, the gas expands from volume V to volume 2V, and the change in entropy is R log 2. Where does that 2 come from? So the thing is that if you go to the molecular interpretation of entropy, then all it says is it's randomness, right? And the randomness is 0 if I have only one possible way to arrange all my atoms, right? So if you think of a perfectly crystalline solid, then there's only one possible way to arrange all my atoms. My atoms are indistinguishable. So I'll not say that this particular atom being arranged here and this particular atom being arranged there gives me a different configuration. No, they are indistinguishable. So all, in mathematical terms, I guess you call it permutations. So I'm not looking for combinations, but permutations. So I have only one possible. And what the statistical mechanics or statistical thermodynamics, what it tells you is, we'll not go into the derivation of all this, but what it says is entropy is essentially R log W, where W is the number of configurations available. Also they say microstates. Okay. So if only one microstate is present, then log W is 0. If W is 1, which means my entropy is 0. And that's what happens for perfectly crystalline substances. The moment you create one defect in this crystal, just one defect. So think of a linear crystal, let's say, and you have the defect at position 1.